All right, this is going to be the lecture over section 17.7. We're going to be looking at electric field lines. Now, what are field lines? Field lines are going to provide a graphical representation of the electric fields. A field line at any point in space is tangent to the direction of the electric field at that point. And the number of lines per unit area that are going to be perpendicular to their direction is going to be proportional to the magnitude of the electric field at that point. Field lines point away from positive charges and go towards negative charges, which you can see here. You can see the electric fields are all going to be tangent to the field lines. You can see it here, that particular point, and you can see where they're all flowing from the positive charge to the negative charge. So the concept here was first introduced by Michael Faraday, and we're going to use the term field lines here to describe this. So you've got your electric field line, you've got your field at this particular point, and that's the vector for it. Same thing here at point R. So field lines never intersect. Where the electric field is strong, we're going to draw a bunch of lines close together. Where it's weaker, they're going to be further apart. And electric field lines have these characteristics. At every point in space, the electric field vector at that point is tangent to the electric field line through that point, which we've already kind of gone over. Number two, the electric field lines are close together in regions where the magnitude of E is large and farther apart where it's small. Again, we've kind of gone through that. Three, field lines point away from positive charges and towards negative charges. That was all developed in the summary. So you can see in this particular part of figure 17.24, part A, you can see where they're emanating, the field lines are emanating from positive charge outwards. That's just a single positive charge. Here we have a dipole, or a positive and a negative charge. At each point in space, the electric field vector is going to be tangent to the field line passing through that point. So you can see a point on the field line here, and you can see the electric field vector pointing this way. That field vector is going to be describing something along the lines of acceleration of a particle in that field. So try not to get confused with that. It can be misleading, but that's what it's trying to point to. If you'll remember back in kinematics, we had vectors for velocity and acceleration, and they didn't always point in the same direction. So it's the same kind of thing here. So try to wrap your head around that. On part C, you can see where the field lines are close together, where the field is strong, and then you can see it's farther apart over here where it's weak. This is an interesting description of a parallel plate capacitor. In a uniform electric field, field lines are going to be straight, parallel, and uniformly spaced. And a parallel plate is going to give us a scenario just like that. If you'll go through here, you're going to be looking at straight lines because it's the most direct path between the positive and the negative charges. All these lines are parallel, and they're all fairly uniformly spaced here because the charges are fairly uniform here. When two conducting sheets carry opposite charges and are close together compared with their size, then the electric field in the region between them is approximately uniform. And this arrangement is often used when a uniform electric field is needed. If you're going to deflect electron beams, I know that parallel plate chambers are also used in the radiation therapy. It's something that the physicists need to use from time to time, and generally it comes around when you have to deal with electrons. So that a parallel plate capacitor usually consists of two sheets separated by a thin insulating layer, and then that forms the capacitor.